All right. I think we're all here, so let's go ahead and get started. Thank you, everyone, for coming. We're going to be talking about lies today. My name is Larry Garfield. You may know me online as Krell. If you want to make fun of me on Twitter during the talk, that's where you do so. I generally encourage it. I'm a longtime member of the PHP community in a number of different roles. Among other things, I'm a member of the PHP Fig core committee. Fig is kind of PHP's de facto standards body, so I've been in that for a while. I'm also the author of Exploring PHP and Thinking Functionally in Exploring PHP 8.0 and Thinking Functionally in PHP. And I'm actually going to be raffling away a copy of Thinking Functionally at the end of this talk. So stick around for that if you have any interest in PHP, which you really should. It's a nice language. But that's not what we're here to talk about. We're not here to talk about PHP today. We are instead here to talk about clouds. Wrong clouds. I actually mean cloud-based hosting, because that's the big thing these days. That's what people talk about all the time. You know, cloud this, cloud that, cloud computing, cloud hosting. Great. What's the cloud? What does that actually mean? Well, usually when people talk about clouds, they're talking about things built with containers. Great. What's a container? Not that. I mean, that's technically a container, but I'm pretty sure that's not the kind of container we're talking about. That's actually my lunch. So no, that's not the kind of container we mean. Oftentimes I hear containers being spoken of like shipping containers, and okay, not quite. Yeah, I don't think that's a server farm. At least I hope not. The ping time is going to be terrible. Oftentimes I hear containers talked about with whales for some reason, and I mean, okay, that's a container for plankton, but probably not the kind of container we're talking about. Often when people say container, what they're talking about is this, and okay, this uses containers, but Docker is not actually what containers are. Docker is not synonymous with containers. Okay, so what is a container? Basically, everything you have been told or heard about containers before is a lie, including the containers themselves. Containers are fundamentally a lie. They're a very useful lie. And that's not a bad thing. In fact, all modern software is built on lies. All Everything you're doing, all hosting systems, all programming is built on lies. So to understand what containers are, we need to first understand all of the lies that build up to containers. And that we're going to start with the very first lie, and that is this a concept of a process. What is a process? Well, this is a CPU. It's a very old CPU at this point. It's an old Intel Pentium MMX. For those of you who remember those, this is the one that can actually do math, not the one that had broken math, to see who's that old. And CPUs are fundamentally single-threaded devices. They have a very basic set of instructions that they can understand that are very low level. Move, add these two numbers, put result here, copy this number from this register to this register, and so on. And they will execute those instructions one by one in sequence. And they have a special register called a program counter that tracks what the next instruction to use to execute is. And some of the instructions go and directly modify that program counter to tell it to skip over or skip back in that list. That's basically what all modern computers do. All hardware these days works on essentially that model. Now, the CPU does a lot of things. It does computation, but it also does I/O. It has to talk to RAM, it has to talk to the hard drive, it has to talk to a network, and that is extraordinarily slow. Talking to even an SSD is orders of magnitude slower than the CPU just talking to itself and doing math. And if you want to actually connect to something on a network and talk to another whole other computer somewhere, even just another one in the same room, to say nothing of across the world, that takes eons in CPU time. So it'd be really nice if the CPU could not sit and wait during that time, if it could do something else, meanwhile, while it's waiting for the network or the hard drive or the sound card to get back to it. Enter an operating system. An operating system, a lot of different on the market, is a very special piece of software, a series of instructions that sits on a computer and coordinates with the CPU. And its primary job, it actually just does a lot of things, but its primary job that we're concerned with is that it is software that manages software. And an operating system conspires with the CPU to lie to you about what series of instructions the CPU is actually running. The operating system has this chunk of it called a scheduler. Again, lots of other pieces. This is the part we're concerned with. The scheduler coordinates with the CPU and manages this thing called context switching. Periodically, the CPU will tick, and when it ticks, it fires a timer interrupt in which the CPU will stop whatever it's doing and update its program counter to say, hey, go look up this exact piece of code out of memory and execute that. And that place in memory has a piece of the operating system called an interrupt handler. That interrupt handler will wake up and go, okay, jump to that program counter. And that's a different series of instructions that program counter is now part of, that address is part of. And this happens over and over again, thousands of times a second, for the CPU to say, oh, wait, operating system, what should I do next? And the operating system goes, that. And this allows you to trick the computer, trick the CPU into working on multiple lines of instructions at the same time without having the programs, without the series of instructions needing to know about each other. Now, these days, most systems have multiple cores, or a lot of programs have multiple threads. Conceptually, what you have there are then multiple program counters. If you have multiple cores, then you have multiple program counters on different, each working on a different stream of instructions. Or you have, in threads, multiple program counters working on a single stream of instructions. Okay, that's great, but how do we keep track of all of that nonsense? How do we keep track of all those program counters and the memory that all of those series of instructions live at? That is called a process. A process is a logical construct that exists in the CPU and the operating system that bundles together a stream of code, a program counter, some kind of ID to keep track of the processes so it can refer to them by some identifier, and a block of memory that the process is working with, where it stores its variables. That's what a process is. It is a shorthand for bookkeeping for all of this stuff. Now, processes, when run in any modern operating system, know about each other. They can ask the operating system, hey, what other processes are running when it's their turn to run, and get back an answer. And they will all get back the same answer. And they can then communicate with other processes by sending them messages through the operating system by saying, hey, send this message to process 47 or whatever. And they can get the same information from the operating system. If process 6 asks the operating system, hey, what's the name of the computer I'm on and does it have a sound card? And another process asks the operating system, hey, what's the name of the system I'm on and does it have a sound card? They'll get back the same answer. Processes can also spawn new processes, either by forking, meaning you take one process, duplicate it in memory, but it doesn't actually duplicate, it just duplicates the program counter, and then those processes continue their merry way. Or by telling the operating system, hey, operating system, you see that file on disk over there? Load that into memory, stick the program counter at the beginning of it, and run, and that's a new process. And in this way, we create a hierarchy of processes where process 1 starts process 2, starts process 3, and process 4 and process 5, and so forth. And generally, the first process that starts after the operating system gets called init. It's the init process. And its job is to control and coordinate all of the other processes. There are a number of different init systems available. On Unixes, the big ones are the old init.d system. Runit, systemd is the big name in the Linux world these days, and so on. They're all doing essentially the same thing. They are a way to coordinate all of these other things outside of the operating system, all of these other processes. Okay. But there's more than just the stream of code, there's also memory, because all of these programs are sharing the same memory. And that means that their addresses need to be different. The physical address in RAM that a program lives at, or that its variables live at, they need to be unique. Are you as a developer going to be able to keep track of, oh, my variable is at address 47 in memory, but wait, the operating system just moved it to make room, and now it's been relocated to address 419. No, you are a human, therefore you are incapable of keeping track of that kind of memory management. So the operating system and CPU, again, conspire against you to lie and tell every process, hey, you have the entire memory from address 0 to address 4 gigabytes, or 2 gigabytes, or 12 gigabytes, or however much RAM you have. And your program can then say, okay, my variable is at address 12. It's not at the real address 12, it's at the fake address 12 that you have. And there's a lookup table in the operating system and in the CPU, so that when your program accesses address 12, that gets mapped over to physical address 419,000 or whatever, because the real address 12 is part of the operating system, and you really don't want to overwrite that. Bad things happen. So every process then thinks it has contiguous memory, even though it really doesn't. Now, those of you who have actually done operating system work are going to point out that I am grossly oversimplifying what's going on inside a CPU and inside of an operating system. Yes, I am skipping over caching details. I'm skipping over complex instruction sets, whole lot of things I'm skipping here, just for the sake of keeping this talk to only an hour. But what if we could tell different lies to different processes? We already said all of this stuff is just lies and lookup tables to keep track of different lies. What if we could tell a different lie to each process? What could we do with that? Enter namespaces, which are a feature of the Linux kernel. At this point, everything we've said up until now is true of pretty much every operating system in the world. From here on in, we're going to be talking about Linux specifically, not GNU Linux, but the actual Linux kernel component. So other operating systems have frequently similar functionality that works very differently in a different model that can do essentially the same thing at the end of the day, but we're going to talk just about the Linux version here. In Linux, it is possible now through namespaces to tell different lies to different processes. A namespace is a way to cluster processes together and say, this group of processes, I'm going to tell this lie to, and this other group of processes, I'm going to tell this other lie to. And there's 6 or 7 types of namespace in Linux at this point. I'm going to go through the big ones that most people actually are going to run into. The simplest is the UTS namespace. The UTS namespace keeps track of the host name and domain name that a computer thinks it is. Basically, there is in memory a global variable that is the host name of the computer. And it's originally set from the etc hostname file, but you can change it in memory. And then it changes for every process. However, if you set up a UTS namespace, then you can create this namespace in just code, in your kernel commands, and then put process 7 and process 8 into that namespace. And inside that namespace, you change the host name and just set it to web instead of my laptop. And you create another namespace and put process 9 into it. And in that namespace, you change the host name global variable to SQL. So now when process 8 asks, hey, computer, what's the name of this machine? It gets told it's web. When process 1 asks, it gets told my laptop, and so forth. The API for these is fairly simple: set host name, set domain name, and uname. Uname as in UTS. UTS stands for Unix Time Sharing System, which is the name that this memory structure was given back in 1971. And it's still here because you can't change APIs. So beware what you name things. They may stick around for a very long time. The next namespace we want to talk about is the process namespace. We said before that a process has an ID that the operating system can use to refer to it, and that the other processes can use to refer to each other. With a process namespace, you can put processes into a bundle, and then inside that bundle, they have a different ID. And that ID is local to that package, to that namespace. So here, process 12 has two IDs. It had the operating system knows it as process 12. It knows itself as process 2. If it asks the operating system, hey, what processes exist on this machine, it'll get told process 2 and process 3, and that's it. It has no way of knowing that process 14, the green one over on the right, or process 1, the red one over on the left, even exist. Process 1 will get told, oh, there's process 1, 12, 13, and 14. Process 14, if it asks, it'll get told, you're process 1, and that's the entire thing. You're the only process running. This is really cool. Now we can isolate processes from each other so that they cannot interact. They can't send a message to a process they don't know how to reference. Cool. One slight problem, though: a lot of the inter-process communication, the way Linux works, happens through a virtual file system called proc. But, okay, what about the file system? How do we split that up? Can we do that? Sure. That's called the mount namespace. The mount namespace is kind of a super chroot. Chroot is a feature that's been part of Linux since forever. I don't even know when it was added. And normally you have your file tree with a root node and then directories off of that. chroot lets you say, for this process and any of its children, move that root node down to this other subdirectory. So the whole system knows about this full file tree, but this one process, its root is this child of that root instead. A mount namespace does more and allows you to assign completely new independent root nodes that do not overlap at all. So you can have a root namespace or a root mount node for the whole computer, and then inside a mount namespace say, oh, it's this other tree that is completely separate and could be a partition on disk, or it could be a file system that's stored as an ISO image or something on another disk. ISO image, kids, that's the file format for CDs. For those who don't know what CDs are, those old big silver discs that people used to use to ship software around and even play music, which is kind of weird. But that allows you to do something like this, where we create two separate namespaces, A and B, and put different processes in them. And we take one file system image and mount that as the root in namespace A, and a different image and mount that in B. And then we have another file system image that we just mount into both of them as a subdirectory using normal Unix umount commands. So now process 4 can read one set of files, and process 5 can read a different set of files, but they can both read stuff in the secret plans image because that's been mounted into both. This means that process 5 can access Voyager and Borg.png and so forth, but it cannot possibly access holiday.mp4. And if you've ever seen holiday MP4, you know why that is a very, very good thing. This also limits what processes can start. We said before that one way a process can start a new process is by pointing to a file on disk and saying, hey, operating system, start that. If it can't point to it on disk because it's in a different mount namespace, it can't even start it. It doesn't know how to reference it, therefore it cannot tell the operating system to start it. This again allows us to further isolate processes from each other. The network namespace, this one's a little bit weird. You first have to understand this idea of a physical device. A physical device in Linux speak is a logical construct in memory that refers to a physical piece of hardware, an Ethernet jack, a mouse, a monitor, and so forth. And you cannot namespace these. However, Linux also has this idea of a virtual device, which is a lie. It is a data structure in memory that looks and acts an awful lot like a physical device, but there's no actual real network jack or mouse or monitor or whatever behind it. Most processes you can actually put into multiple namespaces and you can nest them. Virtual devices you can put into namespaces, but only one at a time. You can also create virtual devices in pairs and then put only one of them into a namespace. But those two virtual devices can still talk to each other even across that namespace boundary. And that lets you do cool things like this. In this case, we have one physical device, ETH0, and we have the operating system. And the operating system knows about ETH0. And then we create two network namespaces, A and B, and create virtual devices, VF0 and VF1, which get different internal IP addresses within the computer. So there's this virtual network happening just inside the operating system. And we put VF1 into one namespace. Then we also create VF2 and VF3 and put one of them into a different namespace. So now process 42 and process 1337 can both listen to a virtual Ethernet device on port 80 because it's a different device, so it has a different set of ports. It's a different IP address internally. So you now have multiple processes listening on the same port. And you have some translation rules in the operating system that tell, okay, if a request comes in via ETH0 and it matches these rules, forward it to VF0, which gets forwarded on to VF1, and process 42 gets it, and then it can respond back. This lets us have multiple processes now that are doing the exact same thing on the exact same port, except not, because of these lies. We also have the user namespace. This is perhaps the most complex and is the last to be added. We mentioned before the processes have IDs. They also have a user and a group that's associated with them. And this user and group affect access control. Generally speaking, a process can only send messages to another process owned by the same user, unless it's owned by root, and then it can send messages to anything. And we say signals here. The most important is terminate to, hey, shut down, but there are other messages too. A user namespace, just like the process namespace gives us a namespace local ID, this gives us a namespace local user. And we can map that local user to global users and vice versa, including root, which means we can set up something like this, where the whole computer has its list of users, root, and then a couple of others. And then we created namespace A, put some processes into it, and map some users across. And so now we have processes owned by a certain user in that namespace and owned by a different user in the global namespace. So globally, certain users can access it, and locally, different set of users can access it. Then we have another namespace that's a sub namespace of that, where we have processes owned by different users that are local to that namespace. You can do some really weird stuff with this. You probably don't want to get too weird, but the main point here is process 37, the green one at the top left, because you can have a root user that is root only with regard to certain processes. So you can have process 37 here owned by user root in the namespace, and it is therefore root and can do anything it wants to process 38, 42, and 43, but not to process 12, because process 12 is not in that namespace. So you can give a process local god power, which is kind of cool. And finally, we need to talk about control groups. Control groups are the only thing I'm talking about here that is not a lie. Control groups are, in fact, scheduler tweaking. We talked before about the scheduler, which works with the CPU to jump between different processes at different times, and it tries to be fair. Figuring out what fair means in terms of making sure every process gets the appropriate amount of time on the CPU is a really tricky problem. And it's really easy for a program to cheat, either deliberately or by accident, by just running away and doing too much. It can fork a lot, so it has multiple processes. It can just be badly written. It can have a slow query that gets locked. There's a lot of things a process can do to take more than a fair share of CPU time for some definition of CPU, or too much memory. Control groups are also defined in a hierarchy, which is totally separate from the process hierarchy and totally separate from the disk hierarchy. It's a completely different hierarchy. And it also lets you define nodes and then assign processes to those nodes and then attach controllers to those nodes. And these controllers, there's a dozen or so that are little operating system routines that can do a lot of tracking or auditing or capping of what processes in that node or its child nodes are allowed to do. For our purposes, the only ones we care about are the control group controllers that allow us to cap how much CPU and memory those processes can use. So we can say, hey, I've got 12 gigabytes of memory on this system, but I'm only going to give 1 gigabyte of memory to all the processes collectively on this group. And that's this other subgroup of that is only allowed to use as much as 25% of that total memory. So even though my computer has 12 gigabytes, these processes are only limited to 1 gigabyte. This is extremely flexible. There's a lot you can do with it. For example, if we have a 4-core CPU, we can say, all right, process 13, that's our MariaDB database, it gets this core all to itself. Nothing else can run on that core. So now nothing else is going to make MariaDB get starved. It has that CPU core to itself. Meanwhile, this other core, we're going to say, all right, all of our Nginx processes live on that core and that core only. They can spawn multiple. Nginx can spawn multiple processes. That's fine, but they're just going to live on that CPU core, and everything else is going to run on the other 2 cores however they want. So now, no matter what happens, MariaDB getting slow will not impact Nginx. The Nginx will still get the same amount of CPU time, and MariaDB, it may lock up itself. A slow query may run wild and slow down the database, but that will not impact any of the other processes on the computer, unless they're waiting on each other for communication, but they're not going to outstarve each other. You could also, instead of making it per core, just say, hey, this process gets 20% of the CPU time, whatever core, doesn't matter. These processes over here get 15%, regardless of core. Again, tons of flexibility for how you can configure this. But it lets you really tune at a fine-grained level what processes are allowed to use what resources. So you may be asking at this point, is it possible to use multiple at the same time? Can you put a process into both a mount namespace and into a UTS namespace? Absolutely. In fact, it's very common to put them into multiple namespaces. You can mix and match, even overlap them. So you have this group of 5 processes that's in a process namespace, 2 of which are also in a mount namespace that they share with this other process, and that other process is in a UTS namespace. You can do some really seriously weird stuff this way that will probably break horribly. So don't get too crazy, but like systemd, for example, does use just selectively certain namespaces. The most common answer, however, is to just use all of them. Take a group of processes and put them into a mount namespace, a process namespace, a set of C groups, a UTS namespace, network namespace, the whole 9 yards. And we end up with something like this, where we have two processes that are in a UTS namespace, so they have a local host name. They're in a local user namespace, so they have local set of users. They have a network namespace, so they have a local network device. They have a mount namespace, so they have a local mount tree, a file tree. They're in a C group, so you can lock them down to having no more than a gigabyte of memory and a quarter of the CPU power, no matter what the CPU actually has or how much memory the physical computer has. But that means we now have a set of processes that only know about each other, can only talk to each other. They have a local root user for just those processes. They have their own complete file tree. They have their own network configuration. They have their own host name. They have no way to get out of that box or even realize that they're in a box in the first place. And they have a finite, restricted set of resources that's smaller than what the physical machine has. And they can tell that, but that's it. But at that point, is that really any different than these processes just being on their own complete computer? Not really. They can find out that they're in a C group, but they can't actually change anything about that. They still are going to share a kernel, but generally speaking, that's it. So really, is that any different than being on their own computer? This seems really useful that we can create a fake virtual computer out of just a pile of lies and bookkeeping by combining all of the namespaces together. This is so useful, we should just come up with a name to refer to this whole pattern of use all the namespaces. You know what? Let's go ahead and call that a container. This is a very nice microphone I've got here, so I'm not actually going to drop it. So thanks, Obama. Now, namespaces are way too fine-grained of a tool for most daily use cases. The API is not great, as is often true of Linux itself. So what do developers do when they have an API that is too fine-grained for what they need and hard to work with? You build an API abstraction layer on top of it. What else? We're developers. That's what we do. There are a lot of these on the market. Some of the major ones you may have heard of. LXC is the oldest. It's written in C and has language bindings, so you can then extend it in a bunch of languages. C, Python, Go, a lot of others. Docker, you've almost certainly heard of, originally began as a layer on top of LXC, but eventually branched off and wrote its own replacement layer, bottom layer to replace LXC. At some point, some of the people working on Docker decided that, or using Docker decided that Docker, the company, was not doing a good job, and so they forked it and created something called Rocket. You may have not heard of Vaga, which is a container system built in Rust. There's even one written in Bash, which is like 150 lines long. I do not recommend using it in production, but it's worth reading just to see how simple a container system can be. Containers do not need to be, a million lines of code and configuration. They can be super simple if that's all you need. Another piece of the puzzle is something called orchestration. When you have a container, great, that's useful, but you may want to have multiple containers and have them coordinate. So you have multiple containers that have network ports talking to each other. So the processes can talk to another container or to processes in a different container over the network, where the network is all a series of lies in the operating system. Keeping track of all of that can get messy super quickly. Orchestration is simply the fancy name for another layer on top of containers that keeps track of lots of containers. Kubernetes is the big name in this space right now. But Docker Compose is the same idea, and there's others as well that you can use. I'm not going to get too far into how those work. There's other talks for those. They are usually grossly over-engineered in my experience, but that's a different matter. You may also often hear about containers being read-only. And we mean specifically here the file system image used by a container in the mount namespace is read-only. Why is this good? It's not required, but why is it good? Well, there are a couple of reasons. For one, the operating system is smart, which means you can create multiple containers off the same file system image, and the cost doesn't go up. The cost is just the one file system image, and all of these containers can recognize, hey, I'm using the same file system image, so I'm not going to duplicate memory. So if you have 15 containers running the same process, then you have that process, the static part of it only needs to be in memory once. Operating systems are smart. So the incremental cost of adding more is very low. If the file system image is mutable, it's going to change out from under you. That gets harder to do. It also means you have no write collisions, because if you have multiple processes in multiple pseudo computers writing to the same file system, you can potentially have collisions, and they may get weird. If the file system is read-only, well, guess what? You have no write, therefore you cannot have write collisions. Also, this, as we said, this means the overhead is trivial, because it's just bookkeeping in the operating system. You can have 50 copies of a process running in separate containers, and it's just an extra entry in a memory struct in the CPU. So unlike running multiple virtual machines where you need a completely separate copy of the virtual machine instance itself, and then a separate copy of the operating system, and then a separate copy of the, you just have a couple of kilobytes of memory. Everything else is the same as just running normal processes, because you are just running normal processes. So they're just as fast as running a process outside of a container, because all we're doing is translating a few lookup calls. A part of the marketing for containers is the idea that you can run them anywhere. You build it once, run anywhere, it's great. This is a lie. This is a complete lie. This is marketing nonsense, as anyone who's tried to run Docker in production will know. The advantage of containers is not the outside. It's not the outside, because Docker, Rocket, LXC, Baga, all of these things all have different formats. The file system image is structured a bit differently. The metadata that goes with it to say which C groups to use, which containers to use, how to configure the process namespace, all of that is different. It's literally like different image file formats. So no, it's not portable. The advantage is on the inside of your container, because your program has hundreds, if not thousands, of dependencies. Even just a simple hello world script has, like, I come from a PHP background. PHP script, you have your code, any dependencies you've installed, the instance of the version of PHP that you're using, the exact version, the exact compiler that was used to compile it, the version of Nginx you're using, the version of the compiler that we used to compile that, any C libraries that has at runtime, like libc. Java, same thing. You have the exact version of the JVM, you have the exact version of your code, the exact version of your dependencies, you have the exact version of libc underneath, all of which have different combinations of versions that could be there, and every combination has a different set of bugs. So you could have trillions of different possible combinations of your dependencies, all of which have slightly different bugs. And this is terrible. But if you take all of the dependencies you're using and bundle them up together into a file system image, which you can then ship the whole image together, then you're shipping a known exact set of every single piece of your chain except for the kernel itself. So there may be bugs in that specific combination of versions, but it's going to be the same bugs on your computer and your colleague's computer and your production computer and your testing computer. So at least it's somewhat predictable. In a sense, what you're doing is static compiling your entire computer. Or as the memes say, then we'll ship your machine to production. That is the idea behind containers and portability, is you're shipping the entire computer. This is also why languages like Go work really well in containerized environments, because they are already designed to have all of their dependencies compiled into a single giant binary. And that means the size of the file system image you need is very, very small. It's just your compiled application plus any text files that go with it. That's it. Any language can work this way. Languages that produce static compiled binaries by default work better. Now, there are a lot of different ways to use these. So I'm going to, just as an example, talk about and compare two different container systems. I'm going to talk about Docker and platform.sh, which is a container-based hosting company that I used to work at until recently. They're still a good company, though. And just compare not better or worse, but see how they work differently. At Platform, their system is built directly on LXC. It does not use Docker. It's fine. And they use squashfs as the file system image. Squashfs is a file system optimized for producing a read-only file system image that is very small and very fast to unpack. It takes longer to zip up, but it's and compress, but then it decompresses quickly and is read-only, which, as we said, is a good thing. And there's no separate orchestration tool. Orchestration is just a built-in part of the whole system. You push code to Git, and the automation system checks the code out, runs a shell script that does some kind of compilation step, which could be compiling Java, it could be compiling Go, it could be downloading dependencies for your Python app or your JavaScript app or your PHP app. And the output of that is a squashfs image. And that squashfs image is then mounted into a container file system in layers, not using anything fancy, just normal Unix umount commands. Your base OS image has a or your application has a file in it in YAML that says, hey, I want PHP 7.4, I want Java 12, I want Python 3.7 or whatever. And then there's a base OS image that gets mounted into the container with that. Into that gets mounted the application image you just built off of your source code. And into that gets mounted a RAM disk for temporary configuration. That's the run directory. And then a network mounted file system for user uploaded files. So you do have some writable area, but it's not where the application lives. That's a separate file system. And so what's inside the container, if you run ls, this is all you get. Platform uses Runit as their init manager. It has a couple of extra layers of processes for bookkeeping. But really, all that's running here is SSH, Nginx, and PHP FPM. That's it. There are thousands of processes running on that physical computer, actually on that VM on Amazon. But inside the container, it looks and acts like a complete system. And you can log in and start processes and kill processes and use it as though it were a VM. But there's only 3 real processes running locally. It also then can deploy as a cluster. So your application has PHP or Java or whatever, and that builds the way we talked about with the base image, your application, and two writable disks. Then your database, well, that also needs a writable file mount for your data. So it's a different base image, but again, a writable file mount and a config directory. Something like Redis has no writable file disk. It's just memory resident. So cool. It doesn't need that part either. All of this can get deployed at once. And when you need to update it, the update process is throw away the old one, install a new one. So you stop accepting requests, go into that container, you mount the user files, you mount the application image, mount the new application image, mount the user files again, and open it up. And poof, you're now running a new application, new version of your application by shooting the old one and installing a new version. You don't need to update things in place. You actually deploy it by shut down, throw it out, install a new one. This can create a problem for a lot of older Java applications that take a long time to start. During that startup time, guess what? Your application is offline. The system can hold requests for a couple of seconds, up to a minute, but if your application takes 5 minutes to start, it's not going to play well in a container environment. So make sure your application does not take 5 minutes to start. It should start fast. In contrast, Docker works quite differently. Docker uses a layered file system and does not actually have an init process. Docker is optimized for having only a single process. You can put multiple processes into the same Docker container, but the init process that keeps track of them and coordinates them and restarts them if one shuts down isn't there by default. So it's possible to break a container a lot more easily if you try to run multiple processes. It also uses a layered file system, which instead of having just you mount different pre-built images together, it works kind of like layering transparencies on top of each other. For the younger crowd, layering Photoshop layers on top of each other. So in this case, we have a base layer on top of which we layer the files from MySQL, on top of which we layer another set of directories, on top of which layer, and so on. And so to a process in this container, in this mount namespace, it looks like one coherent, complete file system. This is very flexible and very good for sharing those low-level layers. So if you have 50 containers, all with the same base image, but then a different second layer there that's nice and small, you only need that one copy of that base image. On the other hand, every layer you have to go through in order to look something up adds time. It adds overhead. So if a process wants to read the etc hosts file, then it'll first look at the combined file system and say, all right, I want the etc hosts file. Get me that. The operating system or the container system goes, all right, is that in the first layer, in the green layer? Nope. No, it's not there. All right, let's check the next layer. Is it there? No. All right, let's check the next layer. Found it. And we'll return the file to you. This is why if you're building a Docker image, a Docker file, the recommendation is to have as few run lines as possible, because every run line creates a new layer in Docker's layered file system configuration. So the fewer lines you have, the fewer layers you have, and the fewer layers you have to go through to access any given file. Which of these is better? Depends what you're doing. If you're doing web hosting, where you have a very small finite number of possible base images, then building larger pre-built images and using normal, boring, fast mounts is probably a better system. If you want to have a lot of highly variable containers that are ephemeral, live for very little time, say you want to run a command line tool locally in an isolated environment, Docker is great for that, and the system platform uses would be terrible for that. There are others in the market too. You may have heard of Ubuntu's Snaps system or Red Hat Flatpak. Those are also container systems, not Docker, not platform, custom built, optimized for not running web services, but running desktop applications, where you bundle the application and all of its pieces into a container image that you can download and run. Different use case, different design, different set of trade-offs, different optimization. And that's fine. Different tools for different situations. So in short, I would encourage you to enjoy your lies, because all software these days is built on lies, from the process on up to cloud computing. And you can just embrace that, because cloud computing, which we're all supposed to be doing these days, according to the market droids, is a multi-layered lie. It is lies all the way down to the CPU. Your job as a developer is to tell lies to the computer, but not to each other, just to the computer. Because remember, everything in computing is a lie, except the cake, because the cake is not a lie. Thank you.
Awesome. Well, thank you, Larry, for that presentation. And if there are any questions from the audience, please feel free to take some time now and ask those in either the chat or in the Ask a Question tab. And just while we wait for those to come in, just a few housekeeping items here to wrap up. So first off, if you're interested in learning any more of Larry's work, by all means, check out his blog at garfieldtech.com or follow him on Twitter at Krell. So I'm just going to post a link here to his website. And then the next Jakarta Tech Talk is scheduled for April 13th when Chad Carlson presents GitOps keeps focus on product, not on infrastructure. And you can register for that using the link I am just about to post now. And finally, we are always, of course, looking for more topics and presentations. So if you're working on a cloud native Java project, not even necessarily related to Jakarta EE, by all means, consider signing up to present a tech talk using the link I'm about to post. Right now, we are booking into June, so sign up quickly and get on our calendar. Larry, I know you mentioned that you had a contest that you wanted to engage in people, so I'll turn that over to you now.
Yeah, so just a quick giveaway. I'd like to give away copies of my book, Thinking Functionally in PHP. Yes, you can do functional programming in PHP. Even if you're a Java developer, I think it's still worth reading. It's been called by some of my readers the only explanation of monads that has ever made sense. So that high praise there. To do that, we're going to do a little quiz. So just whoever gives the correct answer in the chat first wins, and then DM me on Twitter with your email address so I can send you a link for a copy of the book. The question is, of the namespaces we talked about in Linux, which is the oldest? Which was added to Linux first? I did not actually answer this in the talk, but let's see who knows it. Nope, it was not C groups. Any other guesses? There's only a finite number, so you could just mount. You are correct. The mount namespace is the oldest namespace in Linux. So Johnny, congratulations. Shoot me a DM on Twitter at Krell with your email address, and I'll send you a link for the for a free copy of the book.
Well, congratulations, Johnny. And yeah, I think that about wraps it up. Larry, if there's nothing else from you, thank you again for your time today. And we hope to have you back on again.
Sure. Anyone else have questions?
We did have one here in the chat from Mahid, and he says, why does everybody lie? Is it for business? But I'll let you handle that, but I think you pretty well handled that in the presentation.
Yeah. People lying to people is a bad thing. Please don't do it. Software lying to software is how everything works these days. So differentiate between your people and your programs, because people are not programs. Insert sci-fi reference here.
Absolutely. All right, well, if there are no other questions, again, thank you, Larry, and thank you, everyone, for joining us. And we hope to see everybody at the next Jakarta Tech Talk. Bye, everybody.
Take care.